As a result of this process, there occurred the Huronian glaciation,
so drastically
the
that it
most
triggered a
large-scale
global
ice age in
glaciation,
the history of the Earth, which started 2.4 billion years ago and continued for as long as 300 million years. Diggings revealed that in some areas ice caps reached as far as the equator, with the planet almost totally transformed into a ball of ice. It took the Earth 1.5 billion years to go all
Even as scientists and educators, we ourselves are not infallible. And this is a case of somebody pulling a source from a bad source and just repeating it and repeating it. And I would normally let it slide if it was something minor, but this is major, and it's by people who should know better. So it's a big deal in the fact that it's so much wrong information that it just keeps getting repeated over and over and over, which, if I don't nip this in the bud sooner than later, is going to really give future Precambrian geologists a shell shock when they find out that it's not how they've been told it is on the internet. Generally, as we go into the geologic past, the rock record becomes less complete. Less things are preserved, generally. Now, there are big breaks in the field, if you will, on occasion, and the Huronian is one of those big breaks that we have. Really good preservation from about 2.5 billion years to 2.1 billion years. So about a 400 million year time span, almost as long as the entire Phanerozoic eon. But first I need to say something about nomenclature here. When we say Huronian, technically the Huronian is a supergroup of rocks. What does that mean? That means it's a formalized lithostratigraphic supergroup. That means the rocks have been formally delineated, bounded, and named. And the Huronian is at the supergroup level. Now, the supergroup itself is made up of 4 groups. The groups are made up of individual formations, and on occasion, the formations are divided into members. But formations don't need to be further divided. They don't even need to be in groups or supergroups, but in this case, they are. And although the term Huronian glaciation is technically absolutely incorrect and should never be used because that's for formal lithostratigraphy, you're going to hear me use it here for the sake of brevity and because all the misinformation out there uses that term. Just real quick, when we are talking about chronologic, and I'm using this generically, we actually have a formal code that tells us how to name and delineate things called the North American Stratigraphic Code. But for chronological purposes, we do not reuse lithostratigraphic names. The reason being is because that leads to confusion. That's why we developed this code to begin with. When you're talking about glaciations, take modern ones, for example. You usually hear somebody say the Pleistocene or the Quaternary ice ages, which technically is correct because those are chronological units. We don't say the Wedron-Mason glaciation because those are lithostratigraphic units, okay? I just needed to get that out of the way first because that is the first problem with this whole Wikipedia article that just keeps spreading misinformation about this entire thing. That's number one. And oh boy, do we have many more to go. Let's take a quick look at the geologic timescale in a single bar format here. Now, it's hard to imagine the amount of time passing in geologic terms. The Earth is 4,450 million years old, or roughly 4.5 billion years old. That stretch of time is hard to understand. And I'm going to try to put it into a single bar line here. What is more important than understanding the exact spans of time is the relative association. Now, we have the Phanerozoic here, millions of years ago at top. The abbreviation for that's MA. And you can see the Phanerozoic is 541 million to today. Now, some of you may recognize what that is. That is the Phanerozoic eon. That includes everything from the beginning of the Cambrian, or beginning of the Paleozoic, or some people call the Cambrian explosion, to today. The time of macro complex life is all on that one little green bar right there. That represents only about 12% of Earth's entire history. The remaining 88% is divided into the Hadean and Archean eons. You see here, I'm going to just lump them together because it's not the focus of when the Huronian supergroup was deposited. But that time span, those together, is about 45% of Earth's entire history, almost half, right there. Now, the next one is the Proterozoic eon. That's the yellow bar here. That's only slightly less than the Hadean and Archean combined, at about 43% of Earth's entire history. Now, these things can be subdivided. The bold, non-italicized letters are eons. That is the largest block of geologic time divisible. Many of you have heard of the term Precambrian. I still use it. It is not an actual formal term. It's just a generic term that has hung over forever from the days when we thought that the entire Precambrian may have been as long as the Phanerozoic. A more appropriate term would be Pre-Phanerozoic, but we just use Precambrian because it's so ingrained in all of our literature and language and presentations and even papers. Now you'll see here the italicized bold are eras. That's the next down division. And I'm only going to divide out the Proterozoic here because that's where our Huronian supergroup was deposited, in the Proterozoic eon, specifically the Paleoproterozoic era, that first one. This red bar here shows the entire depositional span of the Huronian supergroup within a general frame. All right, it's not exactly 2,500 to 2,200 million years ago, but we'll get into that later. It's, for all intents and purposes, about that long. And you can see that that's approximately a 300 million year time span, just like it said in all the videos. However, it is not 300 million years of snowball Earth, which we'll talk about later. That is the incorrect part that everybody keeps repeating. The Wikipedia article just says the Huronian has a time span of 300 million years. But since the title of that thing is Huronian Glaciation, people immediately think that means 300 million years of constant glaciation. So I understand that misconception. But this entire depositional span of the Huronian spans about 6.6% of Earth's entire history. Now, when I refine the numbers a little bit, it's going to drop to about 6.1%. But we'll get to that when we get to that. Before I continue, I think you need to know a little bit about me and how I know a lot about the Huronian supergroup. And I'm not just some guy looking at sources on the internet and trying to contradict what everyone else is saying. My name is Stephen Bauman. I am a licensed professional geologist in the United States. And the Huronian supergroup is part of what I study. I study Precambrian sedimentary and metasedimentary rocks are specifically what I study. Now, in my efforts there are other things that I study along with it, but that's my primary focus. And I have written geologic guidebooks along the northern shore of Lake Superior and Huron on the Ontario side that include details and outcrops of the Huronian supergroup. I have even taken many of you to these spots in other videos that I have made over the years. I have looked at these glacial deposits within the Huronian, and I can tell you it is not 300 million years of a snowball Earth. So I just thought I'd give you guys a little bit of my background before I start getting deeper into this. I have even assembled chronologic charts using the lithostratigraphic units, trying to correlate them with other time equivalent units in North America and throughout the globe. So I've put some effort into this during my professional career. So anyways, I think that's enough about me. Let's get into what the Huronian supergroup actually is. But in order to demonstrate to you how all this misinformation is actual misinformation, I need to tell you about the Huronian supergroup. First of all, I just need to say it's mostly along the north shore of Lake Huron. The group has been through several orogenies or mountain building events, so it is highly deformed. But what I'm going to show you is what we call a stratigraphic column. It is not a geologic column. That is a term that we as geologists don't really use. It shows you the chronological deposition of the supergroup as a whole. What that means is the oldest is on the bottom, the youngest is on the top, even though in the field they may have been deformed and faulted out of that typical stratigraphy. Now, the Huronian supergroup consists of 4 groups, lithostratigraphic units, rock units. Now, the entire thing is made up of at least 20 formations. The very top unit, called the Nipissing intrusions, some people include in the Huronian supergroup, others do not. So on the charts I'm going to show you, it's kind of set off to the side. I don't consider it either. We are pretty confident that we have a good depositional lockdown of this supergroup. Now, basically, from the bottom to the top, we start to see deposition of this supergroup beginning at about 2,497 million years ago. I'll get into how we know this later. And up to the top, it stops getting deposited around 2,256 million years ago. So that's about a 241 million year span. Now, if you include the Nipissing intrusions with that number jumps to 278 million years of deposition. So that's where that 300 million years rounded generally comes from, and I'm okay with that. And that's just me knowing the details more than people just generally speaking about it. It's a rounding issue. Let's look at the group from the bottom to the top of the stratigraphic column, because that's the order it was deposited in. At the bottom, you see a sedimentary sandstone type unit. It's called the Livingston Creek Formation. I will get into the environment here in a little bit, but let's just go over the rock types here first. Okay, now above that, we get into the volcanics and plutons of this group. And these are all in the Elliott Lake group, that basal group. This is the only group without any glacial deposits in it. And these volcanics and other igneous rocks are known as the Murray Pluton, the Stobie Formation, the Thessalon Formation's the big one. Above that, we start to see clastic deposition, sandstones, shales, and stuff like that. And the interesting thing is, these are often very yellow in color. There's no reds in any of these sedimentary units, and we'll come back to that in a little bit. But as you go up, that's the top of the Elliott Lake group, and there is a bunch of these little unconformities within the group itself, and sometimes even between formations and inside formations that have been recognized. So it's not a continuous depositional thing, but compared to the overall depositional time frame of the Huronian supergroup, we're talking 1 to 3 million years of missing time in between these things here. Now, above that, we have the Hoff Lake group. And at the very base of that is something called the Ramsey Lake Formation. This has glacial deposits in it. Okay, then above that, we get back into sandstones, conglomerates, shales. We even have what's a tectonic fan type deposit called the Awars Formation that's in the Lake Superior area, and things like that. There's no glacial deposits in the vast majority of the Hoff Lake group. It's only at the very bottom. The other sedimentary units in the Hoff Lake group are very typical of near-shore standard marine environments. Now, above that, we have the thinnest group, which is the Quark Lake group. And that, at its base, also has a glacial diamictite or tillite in it, called the Bruce Formation. Now, above that, we actually get the first carbonate unit after a glacial cycle. People who like snowball Earth, that's one of the things they point to are these cap carbonates, above these glacial units. But in the Huronian, this is the only time we see it. We don't see it above any of the other glacial units. Okay, so that's the Espinola Formation. And then above that, we have the Serpent Formation, which is a sandstone. These are all sedimentary rocks. Now, there's a little unconformity above that, and then we get into the Cobalt group. The Cobalt group is the big one. It's probably arguably the thickest overall, but in the Cobalt group, for the first time, what's called the Gauganda Formation, this basal formation, not Gondwana, that's a continent, a paleocontinent. Gauganda is a lithostratigraphic unit. So I know that could be a bit confusing, so I just wanted to clear that up. The Gauganda Formation, its basal member, this is one of those formations divided into members. The Coleman member has 3 distinct glacial advances and retreats within it, and likely sub-ones within that as well. And the Cobalt group is the only group in the Huronian supergroup that has direct chronal equivalents in the Upper Peninsula of Michigan, like in the Marquette Range and the Menominee Range. Older Huronian supergroup deposits in those ranges are absent. They either never were deposited or have been eroded. In the first brook member, the top member of the Gauganda Formation, for the first time we start to see red beds in the sedimentary rocks. That indicates to us that free oxygen started being pumped into the atmosphere for the very first time. And the first brook member is mostly a shale or siltstone in the area. There's no or very little carbonate in this, so there's no cap carbonate here. But the Coleman member has the thickest glacial units in it. And I've taken you to these before in the field, and I've shown them to you. And compared to modern tillites, they are not much thicker or even thinner. So the glaciation, the glaciers when they came through, now remember, these were deposited in a near marine setting. Marine deposits tend to get preserved a lot easier than terrestrial deposits do because of erosion, but their thickness is on par with modern glacial cycles in the Quaternary, plus or minus. We don't get 3-kilometer thick deposits of these tillites, or 4 or 10. It just doesn't happen. And the thickness issue is often ignored by a lot of people. Now, we don't have fossils to really know in this time, so we have to go by other methods. Above that is what's called the Lorraine Formation. This is a sandstone, and this is a sandstone that contains a lot of what people who collect in the area call a pudding stone. The pudding stone is not formalized. None of the Lorraine Formation is divided out into formal units, but it's about the middle of the formation. It's this white quartzite with these red jasper pebbles in it. The Lorraine Formation looks to be deposited in a fluvial stream environment very near a shoreline, slightly on the terrestrial side. The nature of the quartzite is conducive with a semi-arid type regime. So it may or may not have been. It could have been in a colder climate. We just don't have the paleomagnetic data to know that for sure. And, we didn't have land plants here, so we can't use those as some sort of index either. But from a stratigraphic standpoint, it appears that the Lorraine Formation was deposited in a semi-arid environment. There's no glacial deposits in it, okay? Then above that, we had the Gordon Lake Formation, which is locally a carbonate to siltstone and shale. It becomes more carbonate dominant as you get in the Upper Peninsula of Michigan. And to top it off, we have the Bar River Formation, which is almost a repeat in sedimentary environment of the Lorraine Formation. And then on top of that, it's capped with these Nipissing intrusions, which intrude the entire supergroup. So those have to be younger, those Nipissing intrusions. Those are our youngest part of the Huronian supergroup. Now, shortly after that is when it started to be deformed through several orogenies, but those are talks for other times. So you look at our chart here, and you see I have a G1, a G2, and a G3. Those are our three main glacial pulses. Now, this whole thing is constructed chronostratigraphically with relative thickness. So the millions of years on the left aren't exactly million-year spans because it's more based on the actual thickness of the units. So you get a relative feel of the thickness of these units. And as you can see, these glacial units are not that thick. They do not go through the whole thing. It's not like we had, start getting it in the Hoff Lake group and then every other sedimentary unit is a glacial cycle. That doesn't happen. That would be an argument for a snowball type scenario or a prolonged glaciation, but that doesn't happen. We see zero evidence of a snowball Earth scenario in the Huronian supergroup. We cannot draw that conclusion. We do not have enough data. The paleomagnetic data is still being worked out, and the data that we do have has huge margins of error in it because this stuff is so old. But just looking at the rocks and looking at the sedimentary cycles, we can easily come to the conclusion that a snowball Earth type scenario was not very likely. As a matter of fact, a lot less likely than it was in the Neoproterozoic. And you look at the Huronian supergroup overall, and you have those volcanics at the bottom that give way to these sedimentary units. Why is that? Well, that's because the Huronian supergroup formed on what's called a passive margin. The continent rifted there in what is now the Lake Superior, Lake Huron region, and whatever it was attached to drifted away. We argue to this day whether it was the Wyoming Craton or the Kap Val in South Africa or both. But the point is, a rift formed. We can tell that from the deposits. And then after those volcanics, you start to get a passive margin developing. You start to see those typical deposits. And the modern passive margin is basically the east coast of North America, around Florida up to the top of Gulf of Mexico in the U.S. That's a passive margin type environment. After it rifts, it becomes tectonically quiet, and sediments start to form on that platform on the continental shelf. And then you get about 147 million years of a passive margin phase. Just this ocean basin getting larger and larger and larger. Then during the Bar River Formation, during the deposits of that, you start to get passive margin closing type deposits. That's probably why you get a re-depositional environment to the underlying Lorraine Formation. And there were probably sediments deposited on top of the Bar River. It's just that once this basin began to close, they were eroded. They aren't preserved. And then some time passed, about 40 million years plus or minus, and then Nipissing intrusions start to come up. Now, we argue why that happened because we don't have a continental collision at this time. What probably happened was, as passive margins age and part of Wilson cycles, plate tectonics, this is the record that shows plate tectonics or something very similar to it was in operation 2.5 billion years ago. This right here is it. So as you can see here, there's a lot of ages on what I've been showing you. Well, where do we get these numbers from? Well, they aren't just pulled out of our backside here. We date a mineral called zircon, and that's usually used for uranium lead dating. I'm just going to go with that because I'm trying to keep this simple. But anyway, zircons can be used to date rocks, but not all rocks are created equal: igneous, sedimentary, and metamorphic. In undeformed igneous rocks, you pull the zircons, you can get an actual absolute date. That's the date of the igneous rock, because igneous rocks crystallize from melts. The zircon formed with that rock. That's the date of crystallization. But we only really have those at the bottom and at the top of the Huronian supergroup. And for a long time, that was the bracket. That was it. Now, over the past 10, 15 years, people have started pulling what's called detrital zircons. And those are the numbers you see in gray on this column I've been showing you. Now, detrital zircons, how are those different from normal zircons? Chemically, physically, they're the same thing. Their origin is different. Clastic sedimentary rocks are derived from pre-existing rocks. That means any zircons that they contain were brought from older rocks. So the zircons in them are older than when those clastic sedimentary rocks like sandstones and siltstones and shales were deposited. Oh, conglomerates as well. We like to date coarse things when pulling detrital zircons because they tend to be bigger and easier to date, so we go for the conglomerates and sandstones. But you can, if you're lucky, get them from siltstones and shales as well. And you can see that gives you a number, but that is the maximum age. What that tells you is the youngest zircon from that sedimentary unit is as old as the formation can be. It can be younger than that, but it can't be older. But fortunately, we have these basal igneous dated zircons and cap igneous dated zircons. And when we use the detrital zircons, we can see that they fit in really well with the igneous dates. Now, there are some ash beds, like in the Gordon Lake Formation, that have been dated, and you can directly date those as well and get an actual date. So these things fit and line up pretty well. And what that has done is, on the left side of the stratigraphic column, has given us a good date range for these rocks of ages of deposition. We can be accurate to plus or minus usually 4 to 10 million years, somewhere in there. So we have a pretty good understanding of when this thing was deposited and the time spans involved. And it fits a passive margin model in a plate tectonically active regime. Okay, now that I've talked about the stratigraphy of the Huronian supergroup, and now that I've talked about the dating and how we got those dates of the supergroup, I'm going to dive into the glacial part of this, the mythos part of this, and then I'm going to get into this horrible Wikipedia article. But I still need to do some refining here about the actual glacial deposits within the Huronian. Okay, within the Huronian supergroup, we have 3 distinct pulses of glaciation. This doesn't include the subcycles, just the big 3 broad advances. From oldest to youngest, we have the basal Ramsey Lake Formation, which I have consistently called G1 in these slides. Then we have the Bruce Formation, which is G2, and then the Coleman member of the Gauganda Formation, which is G3. Now, these 3 main glacial cycles contain all of the diamictites or tillites within the Huronian supergroup. Now, something to be noted here, I talked about red beds before. I need to define what we mean by red beds. Red beds are not just red sedimentary rock. In the Huronian, there are some sandstones, especially within the Gauganda, that are red in color, but they're not red because of iron. That red is feldspar. As the glaciers advanced over granitoid rocks, they mechanically weathered those, ripping the feldspars out, and they did not have time to chemically alter into clays. So they got reincorporated into sandstone. We call those arcosic or feldspathic sandstones. So rust or iron isn't making them red. What's making them red is feldspar. So you need to understand that. We don't see the first true red beds until the top of the Gauganda Formation in that first brook member. It's also important to note that banded iron formations, the red jasper, are not red beds because that's actually a chert and it's incorporated into the chert, the red parts. When we say red beds, what we are talking about are rusted sandstones, rusted siltstones, rusted shales. They have iron content in them, usually of less than 5%. That's what we mean by red beds. And the only way you get those is if you have free oxygen in the atmosphere. In the first brook member, the Galganda Formation, there are what appears on occasion to be a biff, but it's really not. It's a pseudo-biff. There's not a lot of hematite free in it. It's just slate, and then these red beds, which if you look at them under magnification, are rusty siltstones. So those count as red beds. Those are the first time we see them. Now, the oxygen content in the atmosphere is probably extremely low. We're talking maybe 0.00001%, if that. It didn't really kick into gear until we got into the slightly younger Lorraine Formation, where the base of that has some distinct thick red beds of siltstone and shales. And even then, you're probably looking at 0.1% of oxygen in the atmosphere. So the GOE, Great Oxidation Event, isn't great right away. It's not like we all of a sudden had a bunch of oxygen in the atmosphere that we didn't before. This took a long period of time, over millions and millions of years. But it didn't start happening until these ice cycles stopped. Now, the thing with the first brook member, the Galganda Formation, the one that overlies the tillite-containing Coleman member, is that you look at some of these deposits in outcrop, especially along Ontario Route 638, and you notice that there's a lot of ripple marks that are very conducive, from what I've seen, in very cold, windy environments along a sandy beach, like the sandy beaches of Lake Michigan or Lake Superior in the winter, these hard angled ripple marks. Even though the first brook member is post-glacial, it was still a relatively cold climate then. Now, we may have had ice caps in one or two of the hemispheres, but ice caps don't equal ice ages. So we have to look at the actual rocks to look for things like tillites and drop stones, which are ice rafted rocks. Ice will sometimes pick up rocks, float it in a sea or a lake, and then when that ice melts, it drops it into the seabed or lake bed. Those are drop stones. Now, those are also indicators of a cold climate. Does it mean there's a glacier sitting on top of it? Not necessarily. We have drop stones originated in Lake Superior region every winter. You know, the ice freezes near the shore, picks up a bunch of pebbles, moves out to the lake, thaws out, drops these rocks. It doesn't mean we're in the middle of an ice age, let alone a snowball Earth. You've got to take those stones with a grain of salt, unless there's a lot of diamictites or tillites around. Then you can assume an ice age type environment. But drop stones in and of themselves, especially in a nearshore marine environment where you know you have topography just offshore on the landward side, you got to take them with a grain of salt. So using the tillites within the Huronian supergroup, those three main pulses, and I'm going to even include the entire Coleman member's depositional time span as one glacial unit, even though there are several pulses within it, which I've already discussed. I'm going to get the 300 million year old glacial people a little bit of slack here, and you're going to see, even when I give them as much as I can, we are nowhere near a 300 million year glaciation, let alone a 300 million year snowball Earth. Okay, so I ran the numbers. The Ramsey Lake Formation, when you take the thickness into account and all the detrital zircons and the dating brackets, we come up with a time span of the deposition of that formation of about 7 million years. So that means from the oldest grain being deposited in the Ramsey Lake to the youngest, we had a 7 million year time span. The Bruce Formation, the next glacial cycle, when we do the same thing, we get about 4 million years. And then the entire Coleman member depositional time span seems to be about 16 million years. So it's a big one. You total those up, you only get 27 million years out of 241 million years from the very basal part of the Huronian supergroup to the last known for sure sedimentary deposit. I'm excluding the Nipissing intrusions here. 27 million years out of 241 million years is a whopping 11.1% of the Huronian. Supergroup deposits have any direct evidence of being glaciated. 11.1%, 27 million years. That's hardly anything like a 300 million year glacial cycle, let alone a snowball Earth. And like I've already talked about, I've been to these rocks. Their thicknesses aren't any thicker than we see near shore, either just a little bit in the sea or a little bit on the land side. The chances of there being a snowball Earth during the Huronian, so a snowball Earth type scenario during the deposition of the Huronian is looking pretty grim. Using the stratigraphy, how the rock units being laid down and how they intertongue and interrelate with one another. Using the structural geology, things like ripple marks, mud cracks, stromatolites, which there are some within the Huronian supergroup. And using the dates that we have makes a snowball Earth look like it really didn't happen, because it probably didn't. Now, the only way to know that for sure would be to lock down the paleolatitudes of these formations through paleomagnetic data. Unfortunately, that is very limited as is right now, and what is available has huge margins of error on it. We aren't even sure Kennerland was a supercontinent. It may have been fragments of continents, like we have today. We have 7 continents. Back then, there was less continental crust. We may have had 2 or even 3 land masses. We don't even know whether or not there was one continent then. And there are papers out there based on paleomagnetic data that show that the Huronian supergroup may have largely been deposited in higher latitudes, even occasionally crossing the North Pole. Okay, let's talk about this Wikipedia article called Huronian Glaciation now. The information I'm giving you is accurate as of March 10th, 2022. Just so you know, have some sort of reference here. Most of the stuff I pulled a little bit before then, but I just need to talk about Wikipedia in general and the people contributing. Just because someone is educated doesn't mean they're educated in what they're talking about. Those are 2 entirely different things. I don't go around editing biology Wikipedia pages because I know I'm not qualified to do so. Now, I'm not going to personally ding anyone that I'm going to mention because it's not appropriate, because all I can go by is what I found on Wikipedia about these people. That doesn't mean the information is necessarily accurate there either, or still relevant. So just keep that in mind. I'm just going to give you basic background on what I found while researching the Wikipedia article about Huronian glaciation. The article was apparently written in 2005 by someone named Anthony Appleyard. I couldn't find any more information on this guy. I don't know if he's still even around anymore, but I couldn't even get a basic educational background for this guy. So I dug a little deeper to see if I could find any information on anyone who's been editing it. And that I did find some information on. Dudley Miles is the most recent editor, and from what I saw, his background and education is either history or archaeology. It didn't really specify in the Wikipedia page. Somebody named Luke Searle I also found, and it just says in there he's a scientist as his day job. Doesn't give an educational background. And then there's someone named Tom Reading, who seems to be an astronomer and a mechanical engineer. So those are the names I pulled from the editing backgrounds I ran across. Now, I'm not dinging any of those people. I'm not saying they're incompetent or anything like that. I'm sure in their fields and what they do, they're brilliant people, but they don't do anything about the Huronian supergroup, apparently. I don't see anyone in there that claims to be a Precambrian geologist, structural geologist, or anything like that. And that explains a lot of what's going on. And the term Huronian glaciation, as I have already said, is not a legitimate term for talking about these ancient ice ages. It's more appropriate to use a chronological term like Paleoproterozoic or Siderian period, which is the period where most of these seem to have taken place. That's more appropriate. Now, I did notice that they did cite the original person to come up with this concept of Huronian glaciations, and that was 1907, and apparently that term was used. Here's the thing. 1907 was 76 years before we had our first North American stratigraphic code in 1983. It's an obsolete concept, and to pull from something that old is fine. I have no problem doing that because those early pioneers in the late 19th and early 20th centuries, those guys could do field work. They really could. But they were products of their time, so they used the language of the time, and no one bothered to see if any of it has changed. And there's still people today who use the term Huronian glaciations, which isn't really appropriate. Now, the term Huronian glaciation in the article is also called, and I apologize if I mispronounce this, the Maganian glaciation as an alternative name. That is also not legitimate. That is a formation in the Potsmesberg group of the Transvaal supergroup in South Africa. That formation has glacial deposits in it, just like the Huronian supergroup does. And that was another lithostratigraphic term pulled as a chronological unit. So you can see where we stand here. And that South African tillite that I just mentioned may be equivalent to the Ramsey Lake or Bruce Formation in the Huronian supergroup. It doesn't seem to be correlative to the Coleman member. Based on the literature that I have reviewed, I'm not an expert in the glacial cycles of South Africa or the stratigraphy there. I will readily admit that. The only thing I'm talking about here is the fact that that term, Maganian, is not legitimate when talking about glacial cycles in the Paleoproterozoic ice ages. So that's just a basic background research into this Wikipedia article, which I know is where everybody got this information from. Now, there's one slight little defense for this Huronian glaciation article. Nowhere in it does it say the Huronian glaciation lasted strictly for 300 million years. The way it's worded is a bit ambiguous, so I can see people who don't know anything about the Paleoproterozoic interpreting it that way. This article is extremely brief, it's extremely vague, and it really needs to just go away. I have thought about fixing it myself, but there seems to be a history within this article here of people restoring previous versions, which to me indicates that someone changed something, someone else didn't like it, so they changed it back. And I'm not going to play that game. In my professional opinion, as someone who studies these rocks, this article needs to go away. It's beyond fixing. It just needs to be trashed and redone. More than just a handful of links. The Huronian supergroup is a very complex supergroup. It is not just a simple, easy thing to understand. There is a Wikipedia article on the Huronian supergroup. But if you're going to focus on the glaciations, you need to focus on what we think we know and keep the conjecture out. Now, the original Paleomag data seems to have been mostly done in the 80s and 90s and has died off since then. But we've gotten a lot better about how we do this. And I think it's time we start actually trying to lock these things down, get an actual paleo-wander path. Now, there's some questions that we may not have had a stable dipole then, which is going to make that difficult. But if we did have a stable dipole then, or at least occasionally, magnetic dipole just means, that stylized magnetic bar through the earth that you think of, a north and a south pole type magnet thing, for lack of a better term. But that's not really how many magnetic fields work. But that's a talk for another time. So I think I'm just going to wrap this up there. I think I argue my case enough here as to why this needs to be vetted better. And if you are a researcher researching this topic, I don't hide who I am or what I do. Just get a hold of me. Get a hold of me on YouTube. And if you want, I can send you my common email address, the one I use in case it gets spammed or anything like that. I'm here to give you the information you need. Anyway, that's it. If you have any questions or comments, please leave them below, and I hope you learned something.